Now in this video, we're going to look at definite integrals. So that's where you actually have the bounds. You're actually finding an exact area under a specific curve. You're not just looking for the antiderivative. Of course, we know using the fundamental theorem of calculus, you have to find the antiderivative first and then plug in your bounds. And you're working with definite integrals, you actually have two different choices. So you could basically just calculate the antiderivative like we did in the previous video and just plug in those original bounds. All right, so nothing really different than what we've done before. All right, but you can actually save yourself a step at the end, and instead of going back to x, you can change your bounds to be in terms of this new g of x, and then plug those numbers in instead. All right, and it might be a little confusing reading it, but let's just see how it works in practice. So we'll do one example of each of these. All right, so we're going to do this exact antiderivative. Again, the numbers are here, which means our final answer should be a number. All right, but you could do this without substitution, but just like the very first problem we did in the last video, it's going to be easier if we make u equal to 1 plus 2x cubed. That's going to make du equal to 6x squared dx. And again, just because I don't see exactly 6x squared in the problem, I'm going to solve for dx. All right, so now my problem is going to become x squared, that becomes u, and then dx becomes du over 6x squared. And again, these x squareds are going to cancel, so that's a good sign. Oops, 1/6. And now we can do the reverse power rule. If this is, I add 1 to the exponent, divide by the new exponent, becomes 1 over 36 u to the 6th plus c. All right, and here's where actually these numbers that are right here weren't right. We can't take the 1 and the 0 and plug it into here because these 1 and the 0 relate to our x, not our u. So now we have to undo our substitution. 1 plus 2x cubed to the 6th. All right, so this is our antiderivative of the original function we're working with, and we know using the fundamental theorem, now we can take this and evaluate it at 0 and 1. We don't need the c when we're doing these versions of integration because the c's basically just cancel out when you do it. So I'm going to plug in 1 first. Then I'm going to subtract when I plug in 0. And then just simplify. So it's going to be 1 over 36 times 3 to the 6th minus 1 over 36 times 1 to the 6th. All right, 3 to the 6th, I'm going to have to use a calculator. Is 729 minus 1 over 36. 729 divided by 36 is not a nice number, so I'm just going to rewrite this as 729 over 36 minus 1 over 36 is 728 over 36. And that's some simplifying you can do because they're both even and you can make the fraction smaller. But I think you can handle that part, and just to keep the video a little shorter, I'll leave it at that. But you can see the basic idea, just like we did in the previous video. I find the antiderivative of this expression. All right, I ended up finding that there. And then once I have the antiderivative, the fundamental theorem says I take my top bound, 1, plug it in, take my bottom bound, 0, plug it in, and subtract those two answers. All right, so that's really similar to how we've done every integral problem, just with the added addition of finding the antiderivative, you use substitution. All right, so what's the other way you could do this? All right, we're still going to need use substitution. I have to take this antiderivative. At some point, we'll just do it in a slightly different way. All right, we're looking for something that's inside of another function. We have this expression here that's inside the exponent of an exponential, so that's going to end up being our u. Again, for right now, I'm able to kind of know what they are, A, because I picked out the problems, and B, because I've done a lot of U substitution. But again, don't be scared to, when you're doing these problems yourself, pick a U, see if it works. If not, retry. All right, and you'll get the intuition as you do more problems about what exactly U should be. But du is going to be 8x dx, which means that is dx. All right, so now my integral is going to be x e to the u times du over 8x. And the x's cancel. Oops, 1 over 8. All right, so I turn my expression into an x expression into a u expression, and I haven't rewritten the numbers yet because instead of using the exact numbers I was given, 0 and 1, related to x, I'm going to convert those numbers into values for u. So when x equals 0, which is this bottom bound, I can use this expression here. U is going to equal 3. All right, so when x is 0, u is 3. So now I can put a 3 here instead, because now I can just think about it in terms of u. Same thing when x is 1, u is 7. So instead of thinking about it as my x term, I can think about it using my u term. All right, so instead of having to go back and plug in these x's, and I'm going to have a lot of extra stuff, I can just change the bounds to being in terms of u, and now I can take the antiderivative. Well, the antiderivative of e to the u is just e to the u, and evaluate that from these new bounds, all right, my u bounds and not my x bounds, 3 to the 7th, or 3 and 7. All right, if I plug in 7, I subtract when I plug in 3, and that's basically going to be the final answer. The other way would be you would convert it back to x's, so you'd have 1/8 e to the 4x squared plus 3, and then you'd plug in 0 and 1, but it's basically the same thing. This just requires less simplifying at the end. It requires you to do this extra step here of changing the bounds in terms of u instead of x, but it actually saves you some time at the end. So it's really up to you which one of these you want to do. It's helpful to know both of them. Again, the way they word the AP questions and stuff might require you to know both. But in reality, as long as you can do one, you can do all these types of definite integrals using U substitution. So ask yourself, do I want to re-plug in my x at the end and have a more complicated equation? Or do I want to take the extra time of changing my bounds to be in terms of u? All right, that's an extra step, but it might make the last step a little bit simpler. So it's really up to you which one you want to do. It's just two different options for doing the same thing. All right, so this is pretty much our biggest topic for after spring break, is figuring out making sure we can do substitution with all these different things. All right, it's a really important topic. All right, so what we're going to do for these next 2 weeks is we're going to do a kind of self-paced thing. So everyone in the class will kind of have a series of worksheets to get through. All right, but everyone will move through it at their own pace. One group might get through a worksheet faster than the other. All right, we'll just try to get through all the different ways you can use substitution. All right, if your group gets through everything kind of quicker than I had planned, then there's some extra stuff that we'll talk about in class that you can work on, all right, to help prepare for the AP exam. All right, but this is the basic idea. All right, we have the basics now of substitution, and we'll just keep building on different things we can use it for. All right, different types of functions like logarithms and trig and inverse trig and all this stuff. All right, so we're just going to kind of slowly build up all the things we can use substitution for. And we'll just kind of do it in this kind of slightly different format than we normally do.